Hello, my name is Justin Garenza. I'm a chemistry major and I'm going to be a senior next year. A little fun fact about me is that I currently do research in the Button Labs here at UNC. It's within the Lung Institute and we research novel therapies for cystic fibrosis and other lung diseases. The reason I want to become a chemistry LA is that I think it's incredibly important to give resources to chemistry students that are able to boost their confidence that they can really deeply understand the material and be successful within the course. I think that having a professor or a learning assistant that can sit a student down and show them a problem and say, okay, I know that this might look like a lot to tackle, but here's how we can divide it into little parts, tackle each one of those at a time, and be able to get to the answer. If you show a student how to do that, that can really boost their confidence and show them, you know what, this isn't as hard as it might look, and I'm going to be able to succeed in the course. A studying and learning tip that I'd like to give as a chemistry student is that you cannot get through courses just through memorization. You have to really deeply understand the material. You have to understand what's going on, what could go on, and why it's exactly going on, because on any exam, you could get thrown a bunch of different conditions, a bunch of different tweaks to problems you may have seen before, and if you only memorize the things you learned in class, you're really not going to be successful. Alright, the second part of this video is me walking through a problem. This is from the Chem 262 workbook. Draw the curved arrow mechanism, including all arrows and intermediates formed during the following reaction. Provide the identity of the missing species in the products labeled as X and Y. Alright, the first step that I think is very good to take in a problem like this is that you have to look at your reactant and determine what functional groups are present and what type of molecule is it. Just looking at this molecule, we can see that this is an ester. Alright, so already you know it's an ester. You can start thinking what type of reactions can an ester undergo? What type of conditions do those reactions need to be in for them to take place? And to get that information, we gotta look at the conditions. Alright, NaOH and H2O, we understand that these are basic conditions. Alright. So we've already been given a lot of information, so I'm going to redraw the reactant since we have to do the curved arrow mechanism anyway. And for our first arrow here, we understand that H2O and NaOH, that's going to be deprotonated, and the species that's going to exist is a hydroxide ion. Alright, so we know we have a hydroxide ion present in our solution. And we can start looking at that and thinking, okay, what are some characteristics that a hydroxide ion holds? Well, we can see it has 3 lone pairs, it has a -1 charge. That automatically should make you think, okay, this is going to be a nucleophile. Hydroxide ion is also commonly a nucleophile, so you can get to that answer that way as well. And so we know we have a nucleophile here, and we can look back at our ester and think, all right, where's our electrophile going to be? When we're dealing with carboxylic acid derivatives, our electrophile is going to be that carbonyl center right there. So we can go ahead and draw our nucleophilic attack going to that carbonyl center. And when we attack there, this carbon cannot have 5 bonds to it, so we know that this double bond is going to kick up to give that carbon only 4 bonds. Alright, so let's draw our intermediate. We have our oxygen first, which exists with a -1 charge with 3 lone pairs. We have our hydroxide that just attacked, which is going to be neutral, and then we have our original phenyl group off of that carbon. Alright, so now we gotta look at what will this molecule do. We see that this oxygen has a negative charge, and we know that that's not that favorable of a state for it to be in. We know it's much more favorable for one of these electrons to push down and form that double bond again. That's also a common theme within all of these carboxylic acid mechanisms. Alright, so we have that double bond kicking down. Again, this carbon cannot have 4 bonds, so one of these groups is going to have to leave. You gotta go back and then think about your leaving group abilities. A good way to think of that is looking back at your pKa's. We understand that right here, that's going to have a pKa equivalent to water, so it's going to have a pKa of about 14. And this phenyl group is going to have a pKa of 10. So we know that this serves as more acidic. It's going to be much more favorable for this phenyl group to be kicked off there. Also, you could just look at the products within the reaction and understand that this phenyl group's going to exist separate from that double bonded oxygen. All right, so we understand that's going to be kicked off. Our new products are going to be a carboxylic acid and a conjugate base of phenyl. 3 pairs of electrons on the oxygen, it's going to have a -1 charge. All right, so now we're at the second part of the problem. Provide the identity of the missing species in the products labeled as X and Y. Now, whenever you get to the end of a reaction, you gotta start thinking, what are these two products gonna do if they're in a solution together? Are they gonna exist within these states, and are these the most stable states that those can exist in? One of the first things you should be thinking about is acid-base chemistry, since that's a very quick reaction. And to do that, we gotta look at our pKa's. So the pKa of a carboxylic acid is about 5, while the pKa of phenyl, if this were protonated, it'd be a phenyl, is about 10. So we know that this carboxylic acid with a pKa of 5 is more acidic than this phenyl group. And so, since it's more acidic, it can exist deprotonated more favorably than this phenyl group. So why don't we just go ahead and deprotonate our carboxylic acid using our nucleophile within the phenyl group. And so we can go ahead and draw our new species, a deprotonated carboxylic acid group, along with a protonated phenyl group. Now, based off our acid chemistry and pKa's, we understand that these two species here are much more favorable to exist than these two right here. And now provide the identity of the missing species, X, right here. That is going to exist as a lone pair. And Y right there, it's going to be a hydrogen. All right. Now this problem might look like a lot of steps, might look very confusing, but if you can take it step by step, look at the reactant, the conditions, and then think about acid-base chemistry, it's not as hard as it might seem. Thank you.